What's up, everybody? I'm excited to share that I've created a new podcast called MedTech Unboxed. Join me as we explore how today's MedTech manufacturing technology is transforming the way medical devices are made, one component at a time. My first guest is Adam Steege, CEO of Trio Labs, based right here in North Carolina. Adam and I will discuss how micro metal additive manufacturing is changing the way medical device parts are made. Enjoy. Adam, thanks for joining the first episode of the new podcast, MedTech Unboxed.
Thanks for having me. Glad to be here.
Yeah, I'm real excited to talk about this very interesting technology for micro metal additive manufacturing and how it can really help kind of the next generation of medical device applications. So before we get into some of the technical details on the technology and the resolution and the materials that you use and the applications, if you can kind of just give us a high level of this technology platform for us, and then we'll get into more details.
Absolutely. So the simplest way to describe it is this is metal 3D printing at a micro scale with the precision of CNC. Mm-hmm. And really the major motivation behind that is, my background before starting this company was in medical device design. So I spent a lot of time designing and developing laparoscopic, minimally invasive surgical devices. So essentially, this is the tech that I wish I had when I was doing that work. And that was really the motivation for building this thing.
Okay. And it's referred to as resin-infused powder lithography, RIPL, right?
Yes.
And what can you tell us about that as far as this additive process and the resolution that you're able to achieve when you said CNC quality level, right?
Yeah, no, it's similar to some technologies that I think people are familiar with. And I think the best way to look at this is with respect to MIM. So for example, MIM, you have your metal powder feedstock, you blend it with a polymer, you inject and mold a part, you get your green part and you sinter that. What we're doing is taking the same metal injection molding powders, putting them through a digital fabrication process to make that green part, and then sintering it afterwards. And so you get MIM inputs, MIM outputs, which means you can use the same materials you can use in metal injection molding. So we're really leveraging a lot of the metallurgy, mechanical material properties that have already been established and validated for surgical devices in that space, with the key distinction that because we're fabricating the green part digitally, we can get down to much smaller features than you can get with MIM. You don't run into the same mold flow mechanics that you do with MIM. So things like making a thin section next to a thick section, you get more design flexibility on those things. And of course, you're also more design flexible just relative to what you'd have in a mold, right? There's only certain geometries that you can mold, and really certain geometries that you can mold, economically without having a dozen different side actions, things like that, undercuts and so forth. So there's a lot of things that you can do when it's done digitally that you can't do with the mold, with the yet added advantage that a lot of additive technologies have, which is you can quickly turn around parts, you can iterate on designs faster. So I think that's really the way to look at it. Is we see it as sort of digital MIM in the sense that you can do a lot of the great things that you can with MIM and do some things even better, especially when it comes to prototyping, pilot production, things like that. You're really flexible in terms of whether you're doing one part or a million parts, the technology looks the same. And I think the other thing to highlight with this is we're using a really high resolution lithographic process for producing these green parts, higher resolution than we've seen from anybody else in this space. So we're working with 5 micron resolution in our process, and that's where we get down to CNC quality, right? So when you're getting things like tolerances down to 1 thou or less on parts, when you're getting down to surface finishes that are RA32 straight out of the furnace, no secondaries on the part, then you're getting CNC quality out of that. And that was, I think, the main thing that we focused on. We knew that you'd have to go to a much higher level of resolution than what conventional 3D printing was doing to get something that functioned like a machined part. And so that's what we focused on. And that was the frustration for me, frankly, when I was developing devices, is I love being able to 3D print things, but you'd always get a part that was kind of like the part, but not really the part.
Yeah.
Tolerances weren't there, surface finishes wasn't there, mechanical properties might not be quite there. You had to compromise on a few things just to get quick turn prototyping and maybe some design flexibility. And that was, that's something we really didn't think had to be there. That was something I think that a lot of folks in 3D printing had accepted as just inherent in the technology, and we really wanted to push past that.
Yeah, that's amazing. The 3D printing concept has been so beneficial for MedTech R&D prototyping, but with the drawback of the surface quality, surface resolution, maybe even mechanical properties, right? And
Yes.
to be able to achieve 5 micron, or that's around two tenths, right? Uh,
Exactly. That's our resolution is 2/10. So you can think of parts being built out of 2/10 layers with 2/10 resolution inside that layer. So it's really, really, really high resolution. And we're actually, I don't want to say too much about it yet because we're not there yet, but we are working on even higher resolution versions of this. So there's room for this tech to really do a lot that 3D printing hasn't been able to do before.
What about the turnaround? I know it's still quick turn, fast deliveries. What kind of, I mean, it might depend on the complexity, but roughly the range of turnaround time for complex parts that are miniature.
It's a great question, and we're fairly indifferent to complexity. That's one of the nice things about doing this with the digital process is, with CNC, more complexity means more cutting time, means more cost, right?
Yeah.
That's just inherent in a machining process. Is every time you add a tool path or add a different tool you have to work with, you're adding time to your cutting process, you're adding cost, and potentially adding lead time depending on what it takes for setup and programming and so forth. With ours, if it's a part that's a few millimeters in total dimension, whether it's got one feature or 20 features on it, it's the same overall size part, which means it's the same build time. So it means we can flip parts in the same amount of time. Generally, we're doing 3 weeks or less on prototype orders. So we have a lot of folks that come to us and they want to test 5, 10, 20 parts. Sometimes they want to test 50 or 100. Sometimes they want to do 5 pieces each of, say, 20 different designs. So they can do minor tweaks on a given part and test 20 different variations all in parallel. We do stuff like that all the time. And generally speaking, if we're on the order of tens of parts or so, we can turn around in a few weeks.
Wow. That's excellent. That really supports R&D and MedTech. Good job there. Talk about some of the different material options that are available for this process.
So right now we're printing in 17.4. We're getting ready to launch a 316L very soon. So we've done a lot of development work on that. We're doing some beta work with that with a few customers. We'll have that fully launched within the next few weeks or so, really. So we're doing a lot of work with 316L very soon. 304L we're also working on. And really it's, I don't think it's surprising which alloys we're working with because these are all very common surgical grade stainless steel alloys. And especially given that a lot of the cases that we're serving are areas where it's a really complex part that might have been CNC'd otherwise. And of course, 300 series stainless alloys are pretty common for CNC, medical device components. So we're definitely focusing on those as our, first area to put our attention to. After that, and we get a lot of requests around this already, we're looking at implant grade materials. So things like cobalt chrome, titanium, those are very much in our tech pipeline. Some ceramics potentially. Nitinol is definitely one that comes up in conversation because everyone is always really curious if there's a new way to make something out of nitinol. And what I'll say about nitinol is long term, I think that will be a part of our portfolio. I think that's going to be a longer term project. Obviously, the metallurgy involved in any SMA material is a bit more complex than any more run of the mill material, but that's certainly something we're looking really hard at as well.
Is there any difference in the surface resolution or tolerance levels with the different grades of stainless that you work with? Or
no, that's the nice
I know
thing
you work
is,
with 17.4, but you're in the future with the others.
Yeah. No, that's a great question. I mean, the nice thing about the process is it's fairly agnostic to the material. Basically, if you can make a powder of that material, the right particle size, shape, and so forth, right? Something that's vaguely compatible with the process. As long as you can make a powder for the material that we can then print and work with, it really doesn't matter what that powder is. The powder itself can be made of anything, provided you can make that material into a powder and then sinter it after it's printed into a green part. So there's a lot of flexibility inherently in the technology.
Okay. Is there been any work done for biocompatibility, or is that just at the base level material, or do you have to look at some of the biocompatibility characteristics as well for applications?
So there's really two factors that you look at for biocompatibility. And I will say that our customers are doing biocomp testing on either components or finished assemblies. So we haven't necessarily done that ourselves, but we have other folks doing that on projects that we're supporting. The two major factors that you look at are composition and surface condition, right? So composition is make sure that when you say it's 316 stainless, it's actually 316 stainless. So anytime we qualify new material, we do detailed analysis on composition. And a lot of that comes down to, and this is true for any binder-based process, you want to make sure during that sintering process that no binder is left behind, right? There's no residual material that would affect the composition of that alloy. So we validated that for 17.4. We're seeing great results for that already on 316, but that's a basic part of our validation process, that we make sure that the metal we send to a customer is the metal that we're certifying. Beyond that, surface condition is the other thing you look at, right? You don't want to have surface porosity that could allow for things like bacterial ingress, or in the case of an implant, let's say you had something that's implanted into in the bloodstream, you don't want to have a certain roughness on your surface that could cause hemolysis, things like that. So surface condition, depending on the exact use case, is something we look at. And for a lot of, I would say, incidental contact, surgical instrumentation, the requirements are at a certain level. For an implant, it's obviously at a very different level. But generally what we've found is our surfaces have really no residual porosity in them. We're getting even much higher densities than you typically get out of a metal injection molded part. So 99% density straight out of the furnace typically. And that gives you much better mechanical properties, but it also means that you worry a lot less about porosity in the surface causing any sort of biocomp issues. And even further to that, we've had a few customers that have tested electropolishing on our material. They've seen really great results. And I think that also speaks to the high density that we're getting these parts, which a lot of 3D printed parts, if you electropolish them, you sort of etch away the surface, and you're trying to get rid of some of the surface porosity that is inherent in like laser sintered parts, for example. And when you etch them away, you just find more porosity underneath. And so it doesn't actually improve the surface condition. Whereas with the densities that we're hitting, we actually see really great results coming out of electropolishing. So there's ways that our parts can work native to the furnace sintering process that we've already seen customers get good results with. And there's also secondaries that can be applied in the event that there are particular needs when it comes to surface condition.
Is passivation one of the secondaries as well?
Yeah, we do passivation standard on all parts.
Okay.
And that's just something we do because it produces a nicer surface. You get much better corrosion resistance out of it. It's a fairly straightforward secondary. So on all the orders that we process now that we're helping folks with in R&D, we do passivation as a standard process. And ASTM standard nitric acid passivation that we run, and we have validated that through multiple ASTM corrosion tests and gotten great results. Okay.
Yeah, one thing I learned with talking to a lot of the folks that work with nitinol laser processing of stents, for instance, is how critical the secondary post-processing is, electropolishing, passivation, and the properties and biocomp and all those. So that's why I was asking about that.
Absolutely. Yeah. I mean, corrosion resistance and surface condition, when you're talking about biocomp, whether it's short, mid, or long-term biocomp, those are definitely key considerations.
Okay. Let's talk about some of the applications. I know I was looking on your website, there's a broad range of applications. We'll kind of focus on the power of three and maybe talk about some surgical device applications, surgical robotics applications, which is everybody wants to hear about that, right? And then, maybe some vascular or minimally invasive type applications. If you can kind of go over a few, that would be great.
Absolutely. So I think the common thread in all those spaces is everything's getting smaller, right? There are areas of those surgical or clinical spaces that have been pretty well explored. So if you look at where a lot of this started, you had sort of two different initial vectors, right? You got laparoscopic surgery for, say, general abdominal surgery, things like that. Cholecystectomies, things like that. Those are sort of the beachhead for minimally invasive surgery. And then on the vascular side, in parallel with that, you have things like wires, tubes, balloons, and so forth. Your general interventional cardiology toolkit. Those have both progressed in parallel and in some ways in intersecting ways. And now we have much more complex instrumentation. Laparoscopic has turned to thoracoscopic, has turned into, all kinds of different indications, even, knees and shoulders and so forth. And in a lot of these cases, now you're going from straight sticks to robotic articulated instruments to long flexible natural orifice, endoluminal instruments. And the continuous theme in all of these has been doing more with less. So accessing more anatomy, having more capability within the instrumentation when you get there, so you can expand the scope of different clinical indications that you can address. And that has inherently made much smaller and more complex instrumentation, right? So if you want to access more anatomy, whether it's, instead of just going to the heart, you want to go into the brain now with neurovascular devices. Well, that's really small blood vessels, so you got really small instrumentation. When you get there, you want to do, you can deploy coils and so forth, but sometimes you may want to do more than that. You may want to, deliver therapeutics. There's, I got to be careful here because there's all kinds of use cases that our customers are working on that I can't really talk about, but there's a lot more capability that you can add to those devices. Neurovascular is definitely a big one, even within, say, structural heart or other, EP applications, having multi-lumen devices that have different ways of imaging or interacting with the environment. Other endoluminal devices, transurethral, bronchoscopic, all these different applications in every single case, it's packing more instrumentation into a smaller space that has to reach farther into the anatomy to address whatever new clinical use case you're going after. And that inherent complexity that comes into that leads to a design space that is very favorable towards what this technology addresses. So I think the way we look at this is we sit somewhere between, say, semiconductor fabrication, right, at the nanoscale, and where CNC and molding sort of trail off a bit. You know, when you get smaller and smaller down to only a few millimeters in size for parts, or even smaller than that, that's when, for complex parts, machining gets very, very expensive and very difficult. Mold physics runs into some limitations. You can only mold features so small. You can only pack a slurry feedstock, which is essentially what's being used in metal injection molding, into so small of a cavity or so small of a feature size. So that's where Ripple technology really does well. It's in that mid-range where it's, big enough that maybe, wafer fab isn't the right approach, plus material set usually dictates that, lithography or wafer lithography doesn't quite fit the bill. Small enough that, or complex enough that molding and machining either can't do it or can't do it cost effectively. And that design space in that, 2 to 5 millimeter size range, we see a lot of, even sub 2 millimeter down to sub 1 millimeter in some cases, especially if you're looking at neurovascular devices. That size range for complex metal parts is really underserved. And that's the area that we focus on.
Excellent. One last question related to the integration of these micro parts to a sub-assembly, a catheter, whatever it might be, a surgical. How are they typically? Some examples of how they're joined are they being? Are there applications where polymers are being bonded to them, or how are they secured or integrated with some other devices as a part of an assembly?
Yeah, so there's a couple things that we've seen. It depends on the type of mechanism. So in some cases, if you're talking a steerable catheter, there's often, say, a polymer sleeve that's being fit over it and then reflowed onto it. And that's actually a really cool use case where we've seen customers take advantage of the digital flexibility you get in a process like this, where you can, say, add texturing to the surface of something, right? If you want to have, say, diamond texture on the outside of a part so that when you reflow onto it, you get really good bond strength, trying to CNC all those little features, an actual texture of the surface, I'm not going to say it's impossible, but it would probably be cost prohibitive. But it's something where you can get that feature almost for free. It really doesn't affect the cost of the part very much to add that kind of feature in a digital fabrication process like this. Okay. So some really cool things we see there. And the other thing we see, especially at the smaller size scales, is like one thing to highlight about the technology is it's a self-supporting build process. So you see this a lot with 3D printing, where you get spider web supports or tree supports or whatever it is attached to the part, and you have to break them off and file them down, and then you have issues with surface condition. We don't have any of that. It's a self-supporting process, so you get consistent surface finish all over. That said, sometimes if you want, say, a fixture to be printed integrated into a part with, say, 2 to 3 tethers on a part that can help with assembly, it's one of those where not supports if you don't need them, but if you do want them, then there's ways to design that into a part to provide advantages during the downstream assembly process. And we see that happen pretty routinely, especially with really small parts. So when we get down to like the sub 2 millimeter size, traditionally a lot of those instruments have been assembled, with tweezers under a microscope, essentially.
Yeah,
that is a really painful process. But if you can have ancillary fixturing printed into the part in a way where you can now stack several parts and weld them and then laser off tethers and so forth, later on, that can actually reduce assembly time and net reduce cost for the entire instrument. So that's something where you see customers taking even more advantage of the deeper we get into some of these development projects. Is it's not just about designing the best possible part and taking advantage of design flexibility that way. It's about designing a part into an entire instrument system and an entire assembly system, assembly process, really, that you're trying to optimize for. So there's a ways to take advantage of that flexibility to optimize for multiple different types of outcomes.
Yeah, I'm so glad I asked that question, because design for manufacturability is a hot topic. It's always been a hot topic, but even more discussions lately. And some of the examples you gave of how you could maybe add some roughness or texture to the surface so you have better bonding with the polymer, and examples in a reflow application, that's great. Thanks for sharing that.
We do see that as a continual issue where it's, design engineers and manufacturing technicians can kind of be at war with each other sometimes.
Yeah.
And a lot of it comes down to, design engineer might have a great idea for, here's how I want to design this, and this is going to serve the clinical need, X times better because I've made this really complex thing. And the manufacturing engineer goes, well, how the hell am I going to make that thing? Yeah. And the technician goes, how the hell am I going to assemble this thing? What am I doing with this? So I think a lot of what we see is being able to leverage design flexibility to bring peace between those different parties
Yeah.
can be a really good thing.
Yeah. No, thanks for sharing that. I know that you're excited for the upcoming MD&M Minnesota show coming up next week. So tell people where they can find you and what you're going to be displaying at your booth.
Absolutely. So we're going to be showing off all kinds of small parts. We have a lot of parts that go under a microscope and then on a screen, because if you just walk by, you might miss them. They're all very small things that we're making, but we'll be at booth 2341. So come by, check us out. You can see parts. We'll be handing out sample kits. We'll also have spec sheets that we can share on the materials we provide. And we're happy to talk about any specific projects we have. Our sales folks are all med device engineers, right? So we really try to set ourselves up as a partner that can provide the best coaching, best DFM feedback on how to use this technology, how it's going to be most effective to improving outcomes for the device that our customers are building. So feel free to bring any questions you have by the booth, and we got great people there ready to answer them.
Okay, great. I look forward to seeing you there.
Looking forward to seeing you there too.
All right. Well, thanks a lot for joining the podcast, Adam, and we'll see you next week.
Sounds great. Thanks, Steve.